Hi, I'm Todd Austin. I'm a professor at University of Michigan and also one of the co-founders of Agita Labs, which is a startup that created the TrustForge Secure Computation Framework for Azure and AWS. Today I want to talk about why securing biometrics is critically important and how encrypted computation like that, which is done in TrustForge, can help dramatically improve the privacy of those very critical components in computing systems. Let's get started. So, what is a biometric? A biometric is just some aspect of you that is unique to you. They can be your face, the shape of your face, it could be your DNA. But often the biometrics we use in computing systems today are fingerprints. Your fingerprint is unique to you, and by imaging your fingerprint, we can generate essentially what is an authentication capability, because producing that fingerprint, we know that it is you that is interacting with the system. The challenge here is the security of these fingerprints. If a fingerprint is breached and taken, it's been shown that it's possible to use that to manufacture false fingerprints and do what's called fingerprint spoofing to unlock a phone, for example, or authenticate with a laptop. And there's accordingly lots of concern, with digital payments growing, etc., that these kind of spoofing technologies could be really detrimental to the growth of biometric authentication capabilities. The other thing that I think is really important to point out in this domain is, unlike a password, you can't, if you lose your biometrics, you can't get a new fingerprint, right? You're born with 10 fingerprints, hopefully 10, and that's what you have. And so it's really important to secure these technologies. In a traditional system that can be hacked, the biometrics may be encrypted, but the keys to decrypt them so they can be compared against whatever's being measured for the authentication, those are on the system. So the system is always at risk of losing those fingerprints. So let's see how you can use secure computation like that in TrustForge to help improve the privacy of these fingerprints. When a fingerprint is measured, the way that it is processed typically is through detection of what's called minutiae, where we look for these basic forms in your fingerprint, and we indicate where they are and the direction that they're going, and that this collection of minutiae becomes unique to you. In a secure computation framework like TrustForge, we're going to actually encrypt all this information and then send that over to the computer, which has a database of encrypted fingerprint minutiae inside of it, people that are authenticated to use that computer, and it'll run TrustForge encrypted computation. With encrypted computation, there's no keys in the system, there's no decrypted fingerprints anywhere. Everything is done directly on the encrypted data. So if somebody hacks into the system, they're only going to see encrypted data. This encrypted computation is basically matching up the minutiae and the angles of the minutiae, and then basically doing sort of an error analysis to figure out what's the sort of the computed distance between the minutiae you produce and the minutiae of a particular fingerprint in the database. If you match, then the system will indicate that you've authenticated, and it'll do what's called a safe data release. Now, this safe data release indicates that a matching fingerprint was found in the fingerprint database during encrypted computation, and the encrypted computation ran without any perturbation. Nobody hacked or changed the order of the computation. And then that information is released as essentially just a single bit saying that we've authenticated this user. Now, if somebody hacks into the TrustForge server, first of all, they're not going to be able to see the fingerprints because the fingerprints are always encrypted, and there are no keys available to software to decrypt those. It's only in the TrustForge enclave that it's actually processing that data. So the attackers don't get to steal anything except encrypted data. But they can try to manipulate the computation, like say, oh, even though these don't match, I'm going to return the fact that they do match. And that's where the integrity checking mechanisms inside TrustForge are going to detect that computation has been perturbed, and again, it's going to not authenticate that, even if it indicated that it did match, because the code was changed. It's not going to authenticate that. So The secure computation and safe data release capabilities of TrustForge provide this privacy-enhanced cryptographic strength defenses to ultimately secure and privatize those fingerprints while providing the ability to do authentication of users based on their fingerprints, their encrypted fingerprints that are produced for the system. All right, now let's take a quick look at this TrustForge platform that the GD Labs produces that I'm going to use for the demo that follows. TrustForge is a next-gen security and privacy platform, and it implements these two capabilities I talked about on the previous slide: encrypted computation, where all the computation that occurs in the privacy-enhanced program is encrypted, and there are no keys for software to see the data that it's processing. And safe data release, where if the data owners and the TrustForge user agree on a particular piece of computation, when that computation successfully runs, it's able to release that information to the TrustForge user. In the previous example, that was releasing the fact that, oh, we've authenticated this particular person. TrustForge is available today on Microsoft Azure and Amazon AWS, and it's programmable with existing DevOps languages like C++, Python, and JavaScript. We've worked with our partners to do world-class security validation on this. We've done commercial red teaming with In-Q-Tel and DARPA, and formal verification with our partners at University of Michigan and Princeton University. Over nearly 2 years of effort for the security validation, no vulnerabilities have been detected in the platform as yet. And what I really love about TrustForge and what I'm demonstrating in these sequence of videos that I've been making over the past few months is really the diversity of applications that it can attack. It's really the Swiss Army knife of privacy programming. These capabilities of encrypted computation and safe data release really build the foundation for true flexibility and privacy-enhanced programming. So let's take a look at this demo, the TrustForge demo on minutiae-based fingerprint matching over encrypted fingerprints. All right, let's take a look at this demo. What I've built is basically a database of encrypted fingerprints, their minutiae, and I'm going to run this test, which is going to build my fingerprint matcher. Now, this is all running on TrustForge, so everything is encrypted. It's going to open a contract to get access to the database of encrypted fingerprints. It's going to take this this known fingerprint, which is encrypted, and it's going to compare it against all of the elements in the database. So it loads the fingerprint database, and then starts to do matching against these elements of the database. And it says I found this known fingerprint was found in the database. So this fingerprint would authenticate against the encrypted database. And then I do the test again, and this time I run an unknown fingerprint. This is not in the database. This is a unique fingerprint that's not in the database. And I run it against the entire database. And then all that is revealed in both these cases was whether or not it was found in the database, which essentially authenticates the user. Now, one of the risks of biometrics is something like a supply chain attack, where I come in here and in this line of code, I actually search my database, and this tells me whether or not it's an encrypted variable. It's a TrustForge encrypted variable, whether or not it's found. And then down here, I can use what's called a data grant, where if the code was run without perturbation, I can see just the value of found. But what I'm going to do is I'm a supply chain attacker, and I'm coming in here and I'm going to change the code, and I'm going to very carefully say, if my friend's fingerprint is presented, I don't care if it's in the database or not. You let that person in no matter what. So this is I'm basically breaking the authentication in the system here by giving this one fingerprint special access. But what's going to happen when I run this, it's going to see that known fingerprint, and it's going to try to say, yeah, let this person in. The problem is it's not going to match the integrity checking mechanisms of TrustForge. It's going to say, hey, you didn't run the computation that I expected you to run, so I'm not even going to produce a result. Here you can see the data grant, which could decrypt that one found variable. The computation that was used to produce it was not the same as the data grant expected, and therefore it couldn't decrypt the result. Now when we run the same code with the unknown fingerprint, in this case, I'm not going to try that supply chain attack is not going to try and perturb the computation, and so the data grant still functions in this case. To validate that first one, I've got to go back in and I've got to undo these changes in my code. And when I do that, I have the original code that we agreed upon could be run in this particular case. And then now I can get a safe data release for both of these computations, for the known fingerprint as well as the unknown fingerprint. I think what's really interesting about these computations is they're pretty heavy-duty floating point math with lots of transcendental functions in them too. So they really show off the ability of TrustForge to be able to compute on these heavy-duty computations. Other frameworks like homomorphic encryption and multi-party computation generally don't work well in the floating point domain. So this is one particular demo that is particular just to TrustForge. Well, I hope that demo was enjoyable to watch. And if you'd like to learn more about me, please visit my LinkedIn page. I've gotten some requests for the source code for these various demos that I've been doing for the past few months. And I'll just tell you that they will appear in the next release of the VIP Bench benchmarks. VIP Bench is a set of benchmarks for benchmarking secure computation platforms like TrustForge, like homomorphic encryption, like multi-party computation. So you can find them there at this GitHub link, eventually in the next release. And then if you'd like to learn more about secure computation, please visit this webpage where you can see a class I taught at University of Michigan last semester that dived deeply into all the different kinds of secure computation. And then if you'd like to learn more about TrustForge Secure Computation and how it could perhaps enhance your privacy needs within your business, please visit agitolabs.com. Thank you so much. Take care.